Okay, Assalamualaikum warahmatullahi wabarakatuh. So today we are going to discuss the last subtopic in topic states of matter, which is phase diagram. Okay, so what is phase diagram? Phase diagram ni basically is a graphical summary of the condition at which substance exists as solid, liquid or gas. Okay, basically it is a graph, okay, that can show at which temperature and pressure our substance exists as solid, liquid or gas. Okay, so basically our phase diagram looks more or less like this. Okay, so this is the general shape of phase diagram. Okay, like I have mentioned earlier, it is a graph of pressure versus temperature. Okay, and then it shows us at which pressure and which temperature our substance exists in the form of solid, liquid and vapor. Okay, so there are a few lines that is important in this graph or in this phase diagram. All these lines, okay, is actually separating two regions, indicates that the condition under which of these two phases can exist as equilibrium. So which means that if we have we look at this line, so this line is actually showing equilibrium between solid and liquid. Okay, if we are looking at this line, so this line is actually showing us equilibrium condition between solid and vapor. Okay, while the last line or the last curve actually shows us the equilibrium between liquid and vapor. Alright, so there is another point that is important, which is called triple point. Okay, so triple point is actually condition where all these three phases, solid, liquid and vapor, exist at equilibrium. And there is also a point called critical point. So critical point is a point where beyond the temperature and pressure, the liquid and the gas or liquid and vapor is indistinguishable, or in other words, they becomes supercritical fluid. Alright, so I'm going to show you a phase diagram of two substances. Okay, number one is phase diagram of carbon dioxide. Okay, if you look at the shape of the phase diagram, it looks similar to the one that I have shown earlier. Okay, where it has three regions, okay, solid, liquid and gas, and we have three lines and curves that is separating between this region. Okay, so if we look at the detail, okay, we can see that the triple point of CO2 happens at temperature 56.4 degrees C and 5.11 atm pressure. So this is the temperature and this is the pressure. So the triple point of carbon dioxide is at this temperature and pressure, which means that at this temperature and pressure, carbon dioxide coexists as solid, liquid and gas. If we look at the graph, okay, at 1 atm, which is normal atmospheric pressure, there is no liquid region. Okay, if you look at the line across 1 atm pressure, you can only see solid and gas condition, solid and gas state only. there is no liquid state at 1 atm pressure. So at 1 atm pressure, carbon dioxide does not exist as liquid. Therefore, carbon dioxide does not have normal boiling point. Okay, as we have learned earlier, normal boiling point tu is boiling point at 1 atm pressure. But instead, carbon dioxide have normal sublimation point. Sublimation because from solid changes directly to gas or to vapor. Okay, so let's take a look at phase diagram of water. Okay, phase diagram of water is more or less the same with what I have shown earlier with H2O, but with a little bit different on the details. Okay, let's take a look at the triple point. Okay, the triple point actually happened at 0.0098 degrees Celsius, okay, or 0.01 if we want to round off, and 0.006 atm. Okay, so what happened at 1 atm? Okay, you can see that water can exist in the form of ice or solid, in the form of water or liquid water, and also in the form of steam or water vapor. Okay, so at 1 atm, water have normal melting point at 0 degrees C and normal boiling point at 100 degrees C. Okay, one unusual thing about phase diagram of water, if you notice, is that the solid liquid equilibrium line of water is actually slanting to the left. Okay, if you look at the phase diagram of carbon dioxide or the phase diagram of any other substances, like I have shown you in the general shape of phase diagram tadi, this line usually is slanting to the right or have positive slope. However, for water, this line is slanting to the left or have negative slope. Okay, why does this happen? Okay, okay, like I have mentioned earlier, generally almost all other substances have solid liquid equilibrium lines slanting to the right or have positive slope. Okay, that is telling us that melting point actually increase with increasing pressure. Okay, this is actually a typical behavior of substance because as pressure increase, the particles should be closer to each other. Okay, as pressure increase, the substance becomes compressed. Okay, it becomes more compact. Okay, so the particles should be closer to each other and occupy less space. Therefore, as pressure increase, any other substances will prefer to stay in solid form. Therefore, the boiling point will increase. It is much harder for the solid to be changed to liquid. Water, however, it have opposite behavior. Okay, if you still remember, we have discussed this during the discussion of why ice floats in liquid water. Okay, so what happen is ice will occupy more space since ice have the maximum number of hydrogen bond can be formed, and it leads to an open hexagonal structure. So open hexagonal structure of ice ini requires more space than liquid water. Therefore, as pressure increase, water tend to stay in liquid form because the liquid form will occupy less space. okay, instead of being solid, because ice water or solid water will occupy more space, which is not compact. Okay, therefore it will lower the melting point, because it is much easier for the ice water tadi to change to liquid water when pressure is increased. So that is why for water the line of melting point tadi is slanting to the left instead of slanting to the right. Okay, we have an example here of phase diagram of Zenon. Okay, we have normal melting point and boiling point given, which is negative 112 degree C and 107 degree C respectively. It has triple point at negative 121 degree C and 0.371 atm. Okay, and then critical point pula is at 16.6 degree C and 57.6 atm. So we were asked to sketch the phase diagram for Zenon. Okay, so what we can do to sketch the phase diagram, okay, first of all, let's draw the axis. Okay, so y-axis is representing the pressure in atm, while x-axis represent temperature in degree C. Okay, mind you that this corner, okay, does not necessarily, okay, this corner does not necessarily starts with 0, okay, because we are not using the scale, the correct scale for phase diagram. We are just drawing in order to get the shape only. So we did not start the corner from 0. So what we can do is that we just follow a logical chronology of the numbers in the scale lah. So if we look here, negative 107 will comes first, okay, for our temperature. So negative 107 will comes first, and then followed by 112. 112 should be higher. Negative negative 112 is lower, and then followed by negative 107, and then we have negative 121. Okay, so negative 121 should be much lower, and then we have 16.6 degrees C. So if you look at my drawing, it does not actually follow the correct scale. Okay, we just as long as the number is in the right order, in the right chronology, then it's okay. Alright, so for the pressure pula, okay, we have 0.371 atm, and then we are talking about normal melting and boiling point, which actually happens at 1 atm, so it's much higher, and then the triple point is at 57.6 atm. Okay, so we have all these points. Okay, now we just have to match with the points. Okay, number one, we have normal melting point. So normal melting point happens at 1 atm, and negative 112. So it meets here, more or less. So that is the normal melting point, and then we have normal boiling point, which is also at 1 atm, and negative 107 is the temperature, and then we have triple point at 0.371 atm and negative 121 degrees C, so it meets here. And last one is we have triple point at 57.6 atm and 16.6 degrees C. Okay, so we have all the points here. So what we are going to do now is just to join them. Okay, so this is the triple point, so it should be more or less like this. Yeah. So the most left should be our solid region. So at the middle should be liquid, and at the right hand side should be gas or vapor. Okay, so this is more or less how our phase diagram should looks like. Okay. Alright, next question. Okay, we were asked by referring to the phase diagram given, describe the phase change when the substance is heated isobarically from negative 80 degrees C to negative 20 degrees C at 3.0 atm. So what we are going to do is we are going to refer to the phase diagram. Okay, and we are looking towards the given pressure and temperature. So we have here pressure at 3 atm. So 3 atm should be in the middle between 1 atm and 5.11 atm. So it should be around here. And then it is heated from negative 80 to negative 20. So negative 80 is about here until negative 20 should be about here. Okay, so the question asks us to describe the phase change. So during this period, okay, what happened to our substance? So if we look at the changes, okay, the substance actually goes from solid to gas. Okay, so the answer is from solid to gas or to vapor. So that is the phase change, or from solid to gas. Okay, isobaric means at constant pressure. So the pressure should be constant. Okay. Question B, the substance is compressed isothermally from 5 atm to 10 atm at 20 degrees C. So compress means the pressure will increase from 5 atm to 10 atm, and isothermally at 20 degrees C. So isothermally means at constant temperature. So at 20 degrees C, so 20 degrees C should be around here. Okay. The substance is compressed from 5 atm to 10 atm. So 5 atm should be in around here, bawah sikit daripada 5.11 tu, until 10. So 10 is a bit above 5 lah. Okay, so the question asks us to describe the changes that happens in this region. Okay, so we can see the changes is actually from gas to liquid. Okay, so basically that is how we use our phase diagram, not only to provide us with the information regarding the pressure and temperature, but also the region where our substance becomes solid, liquid or gas.